Welcome back to this third lecture on natural language processing. Today we'll talk about BERT. My name is Mohammed Rida Bouajanek, and I am a lecturer at the School of IT at Deakin University. So BERT is a pre-trained model widely used for performing many natural language processing tasks. So this is what I call the BERT mountain, right? And in my opinion, if you want to understand deeply BERT, right, you need to claim to understand all these concepts here, right? However, BERT relies heavily on what we call transformers, which are the current cutting-edge technologies for sequence modeling, right? I think you can start just by understanding transformers and then jump to BERT, right? But as researchers, I think it's always better to understand all these technologies here. So this is the outline of today's talk. I will first start with a quick recap in which I will describe transformers, right? Then I will present BERT, its architecture, how we input data to BERT, what are the two main tasks used for pre-training BERT, right? What we call masked language modeling and next sequence prediction. Then I will talk to how you can use BERT for your own application, right? For fine-tuning BERT and use it for your own NLP application. Then I will describe experiments that have been performed on BERT, and finally a conclusion. Okay, let's start with this first part, which is just quick recap on transformers that we've seen 2 weeks ago. Briefly, transformers are an encoder-decoder architecture. And this is the architecture given in the original paper. So basically what you have is this part here, which is the encoder part, right? And this part here, which is the decoder part. So transformers are encoder-decoder architecture, right? So for example, you feed some text here in English and you output text here in French, right? Encoding and then decoding. So in details, this is the transformer encoder-decoder architecture. So basically what you have is, as described in the paper, six encoders that are stacked on each other, right? And then the final encoder will output one vector per each token that was given here as an input, right? So for each token, you have 3 vectors. And these 3 vectors, the output of the last encoder, are given as input to each of these decoders here. So this is the global architecture of the transformer encoder-decoder view. So for the encoder part, encoder does 2 things. You have what we call this part here, which is the self-attention, right? So you feed your token here, it goes through this self-attention layer. Then each output vector of the self-attention layer goes into a feed-forward neural network layer. Then this encoder here outputs one vector for each token, per each input token, which goes as input to the next encoder. Okay, so what is this self-attention mechanism? It's basically just an all-to-all comparison, right? Each input token of the encoder is compared to the other input tokens, right? And the basic idea is really to understand from a language point of view what is the relationship between each of the tokens and the other tokens in the sequence. So the self-attention is somehow interpretable, right? For example, you can imagine that this link here represents the semantic relationship between, for example, the token law and the its. So we can understand, for example, that its here is referring about law, etc., etc., etc. So this mechanism is done multiple times, and that's what we call multi-headed attention, right? It's really an important innovation. It's done in the transformer encoder-decoder architecture 8 times. And the author claims that, each different self-attention is capturing a specific and different semantic meanings of the attention mechanism. So you can imagine, for example, that one self-attention is capturing, for example, the grammar relationship. Another one can capture the vocabulary relationship. A third one maybe can capture the conjugation relationship, semantic relationship, etc., etc., etc. So it's really a flexible mechanism for sequence processing. So transformers, they also, have this what we call input layer, So because it's not a pure sequence processing architecture, it encodes or it injects into the embedding of each input token what we call positional encoding, right? So basically, you inject this positional information into the embedding of each token. So imagine this word je, right, has this vector as an embedding, for which we will inject this vector that represents the positional information, right? And once we inject this information, this is the input vector to the first encoder of our encoder-decoder architecture. Okay, so now let's dive into details of BERT and discuss BERT in details. So again, transformers is an encoder-decoder architecture, right? So basically, transformer uses encoder stack to model the input, right? It projects the input into a latent dimensional space, and then it uses decoder stack to model the output, right? This is the basic or fundamental concept of encoder-decoder architecture. So now, what is BERT? BERT is simply the encoder part or some encoders that are stacked on each other. That's BERT. It's as simply as this. So basically, you just, so this is the encoder of the transformers encoder and decoder architecture. And this is the decoder part. BERT is simply this part. That's BERT. So basically, some encoders that are stacked on each other, and that's it. Okay, so if you go on the website, you download BERT, there are multiple versions, but two versions are widely used. So the first one is what we call BERT base. BERT base and BERT large. The basic difference is just the size. So BERT base has a length of 12 encoders that are stacked on each other. So 12 of these are stacked on each other. The size of the hidden vector is 768. I'm not sure why 768, because usually, in machine learning, we use numbers in power of to the power of n, right? But in this case, it's 768. So this is basically the size of the hidden vectors, right? So each output vector here will have a size of 768. So A is the number of self-attention hits, right? Remember, previously in the encoder-decoder transformers architectures, there were 8 self-attention heads. But for BERT base, you have 12 of them. Again, the purpose is really to capture multiple and different, relationships between input tokens. That's the basic idea. So the total parameters of BERT base is 110 million. It's a huge model, right? That's what we call BERT base. So BERT large has a length of 24 encoders that are stacked on each other. The hidden vector is bigger, 1024, right? Is the size of the output here, and all the vectors that are extended between encoders here. And the size of the self-attention heads is 16. So there are 16 self-attentions, right, for each encoder here. So there are two versions for each of these. There is what we call cased and uncased versions. So again, the cased versions is that, the vocabulary of BERT makes a difference between the word the and the word the. So this is the cased version. In the uncased version, these two words are the same, right? So if you go on the website, you will also find multiple languages for BERT. I think more than 50 languages are provided: French, Germany, Dutch, Arabic, Chinese, Portuguese, Spanish, whatever it is. There are also other versions that are not really used, called BERT Tiny, BERT Mini, BERT Small, and BERT Medium. But usually we use BERT Base and BERT Large. So this is the architecture of BERT given in the original paper. So again, what BERT is just encoders that are stacked on each other, right? Imagine that each stuff here is, encoders that are stacked, right? So for each input token in BERT, you will have a hidden vector that is given as output here, right? So basically, if you give as an input 200 tokens, the output will be 200 vectors, okay? And the size of the vector depends on the version of BERT. If it's BERT base, the size of this vector will be 768. So in BERT, there are some special tokens. For example, the CLS token, which stands for classification. Each time you use BERT, you need to feed first the model with this token here, every time, CLS. Then you have your tokens. If you are using BERT for using it with two different input sentences or paragraph or whatever, right? You need to separate your two sources with this special token called separator. And then you feed your second sentence here or second paragraph here. If, for example, you are using BERT for classification, let's say you want to build a sentiment analysis classifier, right? I feed it with a single sentence, and I want the model to tell me whether this is a positive or a negative sentence. What I have to do with BERT is this. So forget this part. Just feed your sentence here, right? So BERT will output, for each output token, a vector, right? So if you are using it for classification, all you have to do is to use this vector here and feed this vector into a classification layer. We will see that later. Does it make sense, guys? Just let me know, please. Stop me if you think it doesn't make sense. So basically, this is BERT. So there are, competitors to BERT, among which Elmo, that I presented in the first talk, right? Elmo relies on LSTM, right? A bi-LSTM, one that looks from left to right, and the other one that looks from right to left, right? And the output is just merged, and that's Elmo. The main competitor to BERT is what we call GPT, proposed by OpenAI. It's main competitor for me. The main difference with OpenAI GPT-2 also, I think that's the current version, or maybe 3, I'm not sure. The main difference is that GPT-2 relies on the decoder part of the transformer architecture. BERT relies on the encoder part. This is the main difference. So GPT is built, again, using transformer decoder blocks, and BERT, on the other hand, again, uses transformer encoder blocks. So GPT is what we call an autoregressive model. It's autoregressive by nature, right? Because you process one token at a time. So BERT is not. BERT can process in parallel the entire sequence. So by losing this autoregression property, BERT is able to look at the same time from right to left and then from left to right. Right. So, for example, the output to this token here is looking to all the sequence from left to right, and also from right to left, and also from left to right. Right. But if you look at the OpenAI GPT architecture, is all this token, for example, is just, or this token, for example, is just getting information from this side here. Right. It doesn't get information from the right side of the sequence. So this is the main difference between BERT and OpenAI GPT-2. So by nature, BERT is a bidirectional model. OpenAI GPT-2 is not a bidirectional sequence model, right? So this is the main difference. Okay, so moreover, BERT can be run in parallel, so all the sequence or all the tokens here can be processed in parallel. OpenAI GPT cannot, right? You cannot process this token here, except if you process this one, and except if you process this one, etc., etc., etc. Right? You cannot use it in parallel. You need to process sequence by token by token. So that's BERT, right? That's BERT. So now let's look at this, what we call the input layer of BERT. It's just this part here. That's the input layer of BERT, or the input representation. So if you have a sequence like this one, right? My dog is cute. Then you have a separator, and you have a second sentence. He likes playing, right? BERT first step is to split. Okay, we will see that. To split some of the tokens that are not in its vocabulary. Remember, it's a pre-trained model. The vocabulary is fixed. Some of the tokens that may not be in your vocabulary, like the word playing, is not in BERT vocabulary. So BERT has or relies on this word piece embedding model that will basically split this token into two pieces, this piece and this piece, and it has an embedding for each of these two subwords or subtokens, right? As you can see here. So this is play, and then it puts this dash dash to indicate that this token here is part of the previous token, right? And it has also a token for this input here. So once it splits a sequence into tokens for which it has an input in the vocabulary, right? It just collects the corresponding embeddings in this layer, right? Token embeddings. Then it adds what we call segment embedding. So basically a vector. So, okay, this is a vector. So each of these is a vector, right? To this vector, BERT will add what we call segment embedding. So it's just another vector to indicate that this token here is part of the first sentence, right? So this is part of the first sentence, and this is part of the second sentence. So that's what we call segment embeddings. So what is this? Sorry, what is this here? It's basically just a vector for which all the inputs are set to 1. Here, it's just a vector for which all the inputs are set to 0. So BERT will automatically learn and understand that a token here is part of the second sentence just by adding this. It learns that. And the token that is here is part of the second sentence. So this is the basic idea of this, what we call segment embedding. But this is optional. If you are using BERT for sentiment classification, you only have one sequence, right, or one sentence. You don't need this. Finally, position embeddings is added, right? So it's similar to the encoder-decoder transformers architecture. It's exactly the same. Positional information is injected into the embedding of each input to let BERT understand or learn the position of each token in the sequence. Okay, so again, CLS, this is a specific input token, and the two sentences are separated by this specific input token, SIP. Okay, BERT vocabulary briefly. Again, BERT is a pre-trained model. Vocabulary is fixed. You cannot extend it or expand it. The size of BERT vocabulary is 3,522, roughly 30K tokens. It's not too big, not too small. So again, how to deal with unknown words that you for sure have in your input sentence. And this is really, for me, a clever idea. It relies on this model called the word piece. Basically, break down unknown words into subwords for which BERT has an embedding. So, for example, the word embedding itself is not part of the vocabulary in BERT, right? The word embedding itself is not in the BERT vocabulary. So how BERT will deal with this? It will just, split it into three components: EM, for which it has an input embedding, BET, and ING. And remember, whenever you see this dash here symbol, it means that this is part of a word that has been split into multiple words. Okay, the first word, I don't know why, but they never add these dashes here. Anyway. Yeah, so a subword exists for every character. Every character, really, if it doesn't find, subcomponents for which it has an embedding, then it will just split it word by, character by character. Here's another example. This word crocodile, right? It will split like this in BERT, right? K, R, O, X, L, D, Y, P, R, O, and at the end X, for which each subword there is an embedding in BERT. Okay, so this is the input. Now you, I think, understand how to import information to BERT and what's the output of BERT. So again, BERT is a pre-trained model. It has been trained on two different tasks. The first task is called masked language model. Here's the basic idea. They took 15% of the word, or they selected 15% of the word and matched them randomly in a sentence. And the task here is to predict the masked word based on its left and right context. Let's take an example. This sentence, my dog is hairy, right? And they did it, in different way. So 80% of the examples, they randomly select a word, or 15% of the words in a sentence. Let's say, for example, they choose the word hairy here, right? In 18% of the cases, they just mask it. And the task is to predict the masked word. In 10% of the cases, they randomly replaced this token. So here is replaced by Apple, right? And they expect the model of BERT to, find or figure out what is the word that has been replaced or that is inconsistent in the input sentence. And in 10% of the cases, the word is not changed. Right? It's hairy, and you expect to recover the word hairy. So this is the first task, called the masked language model to pre-trained BERT. The second task is a next sentence prediction. So for some of the applications, you need to understand or figure out the relationship between two text sentences or two pieces of text. One application is clearly query answering, right, where the first part of your sentence can be a question. Then you put sub, the token sub, sorry, and then you put a paragraph. I call it context. And what I expect in this situation is to find what span or part of your context that may be an answer to your question, right? And you can use easily BERT to perform this task here. So again, in many applications, you need to feed your BERT with two different pieces of text and just try to understand the relationship between these two pieces of text. And one application is query answering or natural language inference. So a language model does not capture directly this kind of relationships, right? And the way they did it is simply by this, right? So you input your first, so the task is really the next sentence prediction. So basically you input BERT with first a sentence, your sentence A, and then another sentence B. And you let BERT to understand and to tell if the sentence B here is the next sentence of the sentence A. Right? So for example, the men they mask some of the words here. Store, he bought a gallon, I don't know what here, maybe of milk. And this is clearly, yes, it's a next sentence. And 50% of the cases, it's not the case. Like for example, the man to the store, separate, penguin, are flightless birds. And this is clearly a not next sequence prediction. This sequence here, or this text here, is clearly not next sentence of this one. So these are the two main tasks used to pre-train BERT. Again, the pre-training procedure, it was done on a corpus of a book corpus, which includes 800 million words, plus the entire English Wikipedia. It contains 2.5 billion words. So basically, to generate each training input sequence, what they did is just they sample two span of text, A and B, from the corpus. The combined length is, okay, so in BERT, the length of the input cannot exceed 500 tokens. I'm not sure why it's like that, but it's like that. 15% of B is the actual next sentence that follow A again, and 15% of the time it's a random sequence from the corpus. Okay, I've said that. And the loss function is basically just, the sum of the mean masked language model likelihood plus the mean next sequence prediction likelihood. And that's what you basically try to maximize during your training phase. So this is for the pre-training of BERT. So now, how can you use BERT in practice, fine-tuning procedure? So let's see some examples. The first example is classification. And let's say you want to use BERT to perform a classification task. For example, you want to do some sentiment, well, just a sentiment analysis classifier, right? So again, in this case, you only need one sentence, right? You have only one sentence to classify. So here, in this case, you do not need this segment embedding part. It's optional. You do not need it. So basically what you do is just you feed BERT with your sentence. Each token here will output a vector. If you want to use BERT for classification, all you have to do is to use the vector that is given as output here, right? And this is the purpose of this specific or special token CLS classification. So this will output a vector, right? And then this vector, you can feed it to a feed-forward neural network, a regular feed-forward neural network for classification layer, right? I don't know how many layers you want to use, but if you are doing a multi-class classification, it's not only positive or negative. What you will have here to learn is a matrix, right? And that part that you have to fine-tune during your training phase. So this is the matrix, the set of weights that you need to recover during the pre-training, during the fine-tuning phase. Right. So this part of BERT is usually let as frozen. You don't touch it, right? Because BERT is already learning a lot of relationships between your input tokens, and that's what it embeds and encode in this output vector here. So again, all you have to do is to learn this matrix here, and then applying the softmax to get probabilities over the outputs. If you are doing a binary classification, all you have to do is, so this is your vector, right? All you have to do is to put all these into a single unit here, and then apply sigmoid. So what you have to learn here is simply a vector, because a vector is just scalar, right? So that's all you have to do. The example given here is a multi-class classification of BERT. So does it make sense so far, guys? Please let me know. This is another example. Let's say you want to use BERT and fine-tuning it to perform this task called name identity recognition. So basically, for your input sentence, you want to know what token is a person, what token refers to a date, what tokens refers to a place, or whatever, time, or whatever, right? So you have your input sentence here. So again, in this case, each output token, right, will output here a vector, right? Also CLS outputs a vector, but now it's not classification, so this part you don't need it. What you have to do in this case is just to learn or to add a classification layer. What is this classification layers? So let's say you have 4 categories, right? So each of the vectors here, you will feed it in this. So basically what you will have here is a matrix that you need to learn, right? Again, a matrix W that you need to learn. That's all you have to do. And then finally, you just apply softmax again, and then you pick just the class that is maximizing your softmax. And it can be 0, for example, here. It means this is not an entity that is recognized in your input text. This is maybe a person. This is a date. This is nothing, etc., etc., etc. And this is an example. So this is a sentence. Jim Henson was a puppeteer. So this has been identified as being a person. This has been identified as being a person. So whenever you see that this token is part of the previous input token, then just output X. So this is nothing, this is nothing, this is nothing, and this final token here is part of the previous token. It's simply as this, if you want to use it for building a named entity recognition tool. Let's say a third example. Let's say you want to use BERT to build a query answering system. So again, in that case, you have 2 input sentences. Again, your input sentences, you need to separate them using this sep token. This is your question, right? So for example, where do water droplets collide with ice crystals to form precipitations, right? That's your question, what you input here. And the paragraph, this one, is what you will input here. So basically, what you are saying in this context or in this application is what span of this paragraph may be an answer to my question, right? And for example, in this case or in this example, this is the answer, right? So basically, you want to know what span of this paragraph may answer your questions. So now how to use BERT for this? You input your question here. You input your paragraph here. They are separated using this sep token. You have your CLS, always you have the CLS input token. Then for each input token, BERT will output something, a vector, a hidden vector, right? So in this application, clearly it's not a classification, so which means this we don't need it. We do not need the question output. We do not need this part. All we need is to use the vectors that are given here as output. This is a specific task because in this context, you need to build 2 classifiers at the same time, trained really at the same time. The first classifier will try to determine among these output tokens, which one is the beginning of the answer. So basically, you will output 2 vectors with probabilities. And the probability here is telling you what is the probability that this token is the beginning of the answer to the question. And the second output vector is a probability distribution over the end of the answer to the question. So basically this entry here, so this is the start vector and this is the end vector. This probability here is telling you what is the probability that the corresponding token here is the end of the answer. So just pick the token that is maximizing the start and the token that is maximizing the end, and this will be your answer. This is how you can use BERT to build a query answering system. So this is an area on which I am heavily working currently. If you are interested, just please let me know and we can have a chat about that. Okay, let's move on. So experiments, that's all, that's it. So if you look at the original BERT paper, it has been benchmarked and compared heavily over many tasks, including the dataset in the GLUE General Language Understanding Evaluation benchmark. So this is a huge benchmark containing many NLP tasks and by datasets, right? I think 9 or 10. I think the original one contains 10 data sets, right? And BERT has been evaluated over each of these tasks. So if you look at the paper, it's interesting to see that BERT is outperforming all its competitors, even though some of the very, very specific architectures, heavily tuned and finely tuned, for each of these tasks, BERT, even though it was trained over a generic tasks, these two tasks, right, the masked language model and the next sentence prediction, but then just fine-tune it over these specific tasks, right, it was able to outperform significantly some of its competitors, right? So this is the base, BERT base, and this BERT large. And that for all tasks, right? As you can see, it's outperforming sometimes really, really significantly, like on this one, all its competitors. Okay, it has also been tested on, this is a widely used data set for query answering called the Stanford Query Answering Dataset Squad. So, and it was compared with, many approaches, specific approaches, architecture designed to deal with this task, right? And as you can see that, BERT large was able to outperform all of this. And what's interesting is that sometimes, and very often, it's even able to outperform the human performance. Right? This is what we call exact match. And this is the F1 score over the test set. So as you can see here, BERT for the exact match is clearly able to outperform humans into performing these tasks. So it's very, very efficient to solve many, many NLP tasks. It's also the case on the Squad 2.0 dataset. It's a variant of this one, which also includes some of the. Okay, so in this task, you have also to say if a paragraph or a piece of text is not answering certain questions. So it's an extension of this one. And again, you can see that sometimes, okay, in this one, it wasn't the case, right, for the human performance. Okay, but anyway, it's also outperforming significantly its competitors, right? It was also, evaluated over the situation with adversarial generation data set, right? Where the basic idea is to give as input, a sentence like on stage, a woman takes a seat at the piano, and what you have to do is to figure out what is the next sentence here. So you have 4 choices. So all you have to do is just, learn these parameters. It's just a vector, right? This is all you have to learn. And then you apply some probabilities over this vector and choose the sentence that is maximizing these probabilities. So also, what you can notice here is, for example, that BERT here is able to outperform a single human expert, but not when you have 5 annotators, right? So, just as a conclusion, BERT is an unsupervised pre-training model, right? It's pre-trained from language model task. It's increasingly adopted in many NLP tasks to solve many NLP tasks. Google Search is applying BERT models for search queries over more than 17 languages now. It's really a major contribution of the in the NLP field, and basically the major contribution is to propose this deep bidirectional architecture from transformers. It really advanced state of the art in many important NLP tasks, but BERT cannot do everything. It cannot do everything in natural language processing. An example of a task that you cannot do with BERT is a language translation, right? Why? Because remember, if I go back here, oh, sorry, yeah. If I go back here, for each input token, you have an output vector. So all you can do is a many-to-many architecture for which the size of the output is equal to the size of the input. If you are doing language translation, the size of the input is not always equal to the size of the output. And this is a problem if the size of the output is longer than the size of the input. So this is an example of stuff you cannot do with BERT. You can do many to one, right? If you are doing classification, this is okay. Many to many with the, okay. If the size of input is different from the size of output, this is not possible. But if the size of the input is equal to the size of the output, you can do it. Many to one, okay, you can do it. One to many architecture, this is also impossible. You cannot do that, right? You cannot use BERT to generate text. This is just impossible. Because, for example, if you're trying to generate text, it means you will feed your BERT with, I don't know, like a random vector here. It means nothing. You cannot generate text with BERT because there is nothing to learn from an empty input, right? And that's BERT. So just keep in your mind that BERT is fine to solve many NLP applications, but you cannot use it to solve every NLP problem or any NLP task. So you can go on my website, get this set of slides. There are a lot of references that I use to build this presentation. I give them here. And that's it. So if you have questions, just feel free to contact me or to email me. I will be more than happy to interact with you guys. Thank you.
Thank you, Reza, for the great presentation. So I have a little question, and it's about, you mentioned that BERT is used for around 50 languages.
Yes.
And my question is there any structural difference between two different languages, or it is just the, the semantic relationships that is going to be different?
Okay, so when I say two things, okay. So when I say multiple languages, when I say multiple languages, it means it's also pre-trained over tasks specific to each of these languages. You see what I mean? So the pre-training also is done over multiple, over each of these languages with its own data sets.
Right.
Right. So for example, okay, the pre-trained or the pre-training is done over, is done over the English Wikipedia for the English version of BERT. But if you look at the French one, or the Persian one, or the Japanese one, or the English one, it's done over, I don't know, the corresponding language. Right? So it's really learning information, semantic information, and the relationship between tokens in the specific language. So this is the first part. The second critic is for this word piece model, which is a model that has been developed for English. Is it applicable for Japanese or Chinese, in which the tokenization is clearly not the same? Probably no. Right? So, yeah.
So I think Peter has a question.
Yes, I do. Thank you very much for your talk, Reda.
Yeah.
Listen, you're talking about the many-to-one kind of problems, that question and answering problems that BERT could solve. So that's sort of like, I guess, Q&A, like how much does it cost for a taxi from where I live to the airport? And
yes.
It just, and just comes up with a, quantity. And my understanding is that BERT's really good at doing that, right?
Yes.
Right. Okay. And the other thing I wanted to ask you was, do you know anything about conditional random field?
Yeah, CRF. Yeah, CRF. Yeah.
Can you tell me anything to explain that just quickly?
So conditional random field is part of graphical models. It's a really different one. It needs a presentation itself, but conditional random field is probabilistic model, right? So basically, in conditional random field, you have to build this Markov network,
right?
And you have your tokens here, and you have some probability, and you have to infer. I'm not sure you can. Okay, I'm not sure you can. Or I don't know how to use conditional random field to solve the query answering problem. But conditional CRF is widely used, for example, to perform name identity recognition, right? Because you have your input tokens that are here, and you have some corresponding probabilities, right, or factors that are defined here. And the basic idea is to say, right, so what is the probability? What is the probability, that this, okay, so this is what we call the observed, so this is what we call the observed feature in the CRF, and this is what we call the latent feature, right? And basically you are trying to predict this probability here. So what is the probability that, this token here is maybe a person, given that you have observed all this?
Are you writing a conditional probability somewhere? Because I don't think we can see it.
Can you see my screen?
No.
Oh.
Maybe I have to press play or something.
Oh, come on. Can you see it now?
No, I can't.
We just see the BERT.
I don't know what's going on.
Final slide.
I don't know what's going on with this. Can you see it now?
That's the way.
Yep.
Yeah, so, basically in conditional random field, if I correctly remember, it's a Markov chain model, right? You have some states that you observe directly and some states that you do not observe, if I remember correctly. So, and basically what you have to infer here is what is the probability of, this token here. So this is the token being maybe a person, given that you are observing this distribution of words here. Right? And basically, you also infer the relationship that maybe, this token here is also a person, this token here is nothing, right? And you try to figure out or infer this probability of this token here being a person, given that you have a person that is here, maybe not a person is here, etc., etc., etc. It's probabilistic based model.
Got it.
It's completely probabilistic based model.
Maybe others have questions. I'll keep quiet.
Yeah.
Yes, David. Yeah, David is.
Hi, Reda. Yeah, just leave your slides on there. I just got a question on the details. So you show us you have these.
Can you see?
Hi, Reda. Can you hear me?
Yeah, I can hear you.
Yeah. Okay. Sorry. I put my microphone away. So you had these embeddings. You have a token, segment, and positions, and you said that you add them up. Are you doing it numerically? So is it numerical vectors? Are you adding up these values?
Yeah.
Okay, so how does that help you to, when you add the values, you change the values of the vector, does that still give you information about the segment and the position? Because when you add something up, it's kind of all washed into the final vector, isn't it?
Yeah, so, okay, so the vector that is added here, okay, so let's start with this. So the vector that is added here for the second sentence is just a vector for which all entries are 1. So BERT can understand that maybe the magnitude of the vectors here is slightly higher than the magnitude that is here. of the vectors that are here, right? Because what you add here is a vector for which all entries are zeros. So basically you add 0 to this. But here you add ones. Does it make sense?
Okay, so with the positional embedding, is it something similar? So will you add 0, 1, 2, 3, 4 rather than 10?
Similar. Yeah, it's something similar. So basically, you know, so this is something I think they use from the Fourier theory. But basically what you are trying to do is to add, you know, it's in my previous talk, but basically what you try to add to this vector here, to the embedding vector, some positional information that can be like this, right? So you just add maybe, if the token is at the beginning like this one, right? What you are adding is an embedding vector that contains the positional information for which maybe all these are zeros. But the magnitude here is slightly higher than what you have here.
Okay.
You see what I mean? So you let the model by itself learning that this token here, because you know the input is here, the values here are slightly higher, distribution is slightly higher than what you have here. It means probably this token here is at the beginning of your sentence.
Okay. Okay.
But in this case here, sorry, in this case here, what you add here is a vector of ones. All entries are ones, and here all entries are zeros. So the model will understand that, you know, the tokens that are on this side, their magnitude is slightly, distribution is slightly higher than the magnitude of the vectors that are on this slide. So that way, BERT can understand or learn that these are two different sentences, and this is the center, or these are the tokens coming from sentence A, and these are the tokens coming from sentence B.
What if you have more than 2 segments? If you have, say, 3 or 4 segments?
You can't.
So will you add 0, 1, and then -1 or 2 or something like that?
You can't have 3 segments. BERT does not allow you to do that.
Sorry, you only can have 2 segments, is it?
Exactly. 2 segments or 1. One segment.
Okay, all right.
And just keep in your mind, yeah, no problem. Just keep in your mind that the input of BERT is limited. So the size of the input is only 512 tokens. I don't know why they did that like that, but that's the maximum you can put.
Okay, right.
Is there any other question? So Reda, I think there are some texts in the conversation section as well. I think it's interesting to have a look. And if there is no other question, we can finish the session today. I'll publish the link for downloading or watching again soon. So you will have the link to watch all last 3 presentations by Reda, which has focused on natural language processing. Thank you very much for your attendance and have a great time.
Thank you, guys.
Thanks, Reda.
Bye.
Thank you.